going to tell you why it's my favorite section. We're just going to talk about it. And then as things like pop up, I'm going to get excited. Okay. So fair warning, but there's some really neat stuff. So remember polar form, right? Is instead of expressing something in terms of x's and y's, we talk about things in terms of r and theta. It's radius, it's distance from the origin. And theta is the angle that it makes if that were the terminal side. Okay? Yeah, chapter 10 is usually a lot nicer for most people than chapter 9. Actually, chapter 8 is pretty... So chapter 7 and chapter 10 are kind of easier. And 8 and 9 are usually way harder. I was actually surprised, though, at how well you guys did with chapter 8. That was like graphs of functions and like the inverse functions. I was surprised by that. So now we're going to be sort of talking about this in terms of complex numbers. So also, if you remember back to algebra, remember how we used to have these dividing problems? If we wanted to divide complex numbers, it was really tedious, right? We had to multiply the top and the bottom by the conjugate. We had to FOIL it out. We had to simplify with the I-squareds, combine like terms, then eventually express it in the right form again. All right, this was tedious. But today, if we write these complex numbers in polar form, this becomes super duper easy. All right. Also, say I asked you to do something like this. If you had to do this by hand, it would take forever. Super tedious. But this also today is going to be super easy by the time we're done. So there's some neat operations that are a lot easier if you move these complex numbers into a different form. All right. So here we go. Let's talk about something called the complex plane. How do we graph complex numbers? We can graph real numbers on the number line. But complex numbers have two parts, a real part and an imaginary part. So the complex plane is just a plane where this is called the real axis, and this is the imaginary axis. So to graph a point like 2 plus 3i, we just find the point where the real value is 2, and the imaginary part is 3. This is how we plot the point 2 plus 3i. Okay? Just plot the x-coordinate is the real coordinate, and the y-coordinate is the imaginary part. So it's just 2, 3, and that's the complex plane. So there's a very graphical and geometrical nature of all this complex stuff that we're going to be talking about today. So, you know, with that in mind, right, if I said example 1, plot the following, plot 1 minus I, plot 2, plot 3i, and plot 2 plus I. So to plot all this stuff, you just really plot it the same way that we've plotted stuff before. Okay? So again, this is our real axis down here. This is the imaginary axis up here. And all we do, just plot it like normal. 1 minus I. The real part is 1. The imaginary part is minus 1. That's part A. 2. The real part is 2. The imaginary part is 0. So notice, right, for real numbers, 2 is a real number. We just plot it on the real axis, and it's just like the number line. For real numbers, it's just like the number line. But then for complex, non-real numbers, we have to extend it to a plane. All right. This is B right here. 3i, the real part is 0. The imaginary part is 3. 2 plus I, real part's 2. Imaginary part is 1. All right. So that's what it looks like to plot complex numbers. So hopefully you can start seeing where this is going. Right? If we're plotting things on the complex plane, Currently, we're plotting them like with Cartesian or rectangular coordinates. But could we not also talk about this in polar coordinates? Okay, right? So if we talked about this point with polar coordinates, right, there's that angle and that radius, and that's where this is going. Okay? So real quick, let's extend some more notions. The absolute value or modulus of a complex number. It's just the extension of what it is for real numbers, right? The absolute value for a real number is just its distance from 0. All right, so the absolute value of -2 is 2 units away from 0. Okay, something like that. So similarly, the absolute value of a complex number, by the way, z, is very common for complex numbers. Z is equal to a plus bi is super common notation. All right, it's just the distance from the origin. So the modulus, or the absolute value, is just that distance. Okay, it's the radius in polar coordinates. Okay, so nothing groundbreakingly new so far. We're just introducing some definitions for what we're going to be talking about. So let's solve a problem with this. Example 2. Find the modulus or absolute value of z for the following. If z is the square root of 5 minus I, that's just the distance from the origin. It's just the length. It's essentially Pythagorean theorem, right? Also, I should probably include this. So if you want a formula, the modulus of z is the square root of a squared plus b squared. Again, this is really just Pythagorean theorem, isn't it? Right? The distance between a point and the origin is going to be the real part squared plus the imaginary part squared, and that's going to be that hypotenuse squared. So to just solve for that hypotenuse, you just square root both sides. Okay. So the modulus of this z is the real part squared, so square root of 5 squared, plus the imaginary part squared, then that's -1. So the important thing is here, right, that this is the b value, is a coefficient of I, not including I. Do not put i's into this formula for the modulus. Okay, watch out for that. So then you just simplify, right? Square root of 5 squared is just 5. -1 squared is 1. And we get the square root of 6. That's the length, or the absolute value, the modulus of this complex number. Okay. So again, we're just going through these definitions pretty quickly so we can get to some more interesting stuff. All right, we can do that with part B. Z is 3 minus 4i. We just do the same thing, right? So the modulus of z is the square root of 3 squared, which is 9, plus the square root of -4 squared, which is 16. This has length 5. And again, it makes sense, right? The real part's 3. So if we plotted that, right, you go over 3. The imaginary part is -4. So right 3, down 4. It's like we have a little triangle right here. Right? It's kind of like a 3, 4, 5 triangle. Okay, modulus, absolute value, just the distance from the origin. So, kind of alluded to it, but now let's I'll straight up say what polar form is of complex numbers. Right? So if we have a number a plus bi, right? Well, then a is the real part, b is the imaginary part, the modulus is the hypotenuse. Or if you want to use r, we're going to be using r a bit today. We used r for polar coordinates before, right? Then what is this in polar form? Well, the x coordinate is a. What's the x coordinate? Remember? X is r cosine theta. We said y was r sine theta. This is what we talked about in the last section. So a, right, z is a plus bi. And a is our x coordinate. That's r cosine theta. Plus b is our y coordinate. That's r sine theta. Times that I. And this is essentially polar form. Usually we rewrite it a little bit. We factor out the r. We have cosine theta. And then we almost never do this except for polar form of complex numbers. We write the I in front. So this right here is polar form of complex numbers. This is standard form. There's also a shorthand that we're going to use here. And the shorthand is writing it z is equal to r cis theta. Where this is just a shorthand right here, right? For cosine plus I times sine. CIS, cosine plus I times sine. Okay, it's much quicker to write things this way. Pythagorean theorem is going to pop up everywhere, yeah. Absolutely. More notation again. We said this is the modulus, or the length, or the absolute value. This is the angle. Also, it's sometimes called the argument. Okay, anyone familiar with computer programming and stuff? Will also be familiar with argument as like the input of a function. It's something similar here. Okay. Theta is often called the argument. I usually call it the angle personally, but you may see this, so watch out for it. All right. So let's start actually working with this stuff. For the rest of the class today, we're going to first move things between forms. Again, we haven't gotten to the really exciting stuff for me yet. We're going to move things between forms just to make sure that you know, okay, how do I get things from this polar form, and how do I get things into rectangular form? And then we're going to talk about a bunch of really neat properties that pop up when you write it in this form. There are some really cool things that happen here, okay, that make working with complex numbers in polar form both a lot of times easier and sometimes even more intuitive. Sometimes. We'll see. Okay, so example 3. So this is a shorthand. Yeah, exactly what Ashton said. This is just shorthand right here. And it stands for cosine plus I sine. So these are the exact same thing. These two boxed things mean the exact same thing. This second thing is just shorthand though. Okay. So, because writing this whole thing out takes a fair amount of time, and some people use shorthand. Funny enough, by the way, I had never heard of this shorthand until teaching this class. But I asked some other math professors, and they said it's common shorthand. A lot of the people who went to college in like the later 80s and 90s, they saw it a lot. And then people see it in higher level math classes as well. It's not very common for for a trig class, but I don't see any reason not to include it. It's just shorthand, and it makes less writing. So you don't have to use it though, but I will use it because I'm lazy. But feel free to ask me if you forget what the shorthand is. I'm not requiring you to remember the shorthand, but it's kind of nice. So express in polar form. Part A. How do we express the number 4i in polar form? Well, this is polar form. We need the r, and we need theta. Ashton, you never would express it as cosine minus I sine theta. You would never do that because we can incorporate a negative right here in term if sine, right? If we wanted to do a minus sine of 90 degrees, sine's odd, right? We would just do plus sine of negative 90 degrees or something like that. So this is the standard form right here. The standard form will always have a plus, which is why we don't need to include the plus in the shorthand. The negative is a part and is taken care of by the angle here. That's a good question though. And I think we'll see that. Actually, I mean, we can see it right here. Let's change the problem to negative 4i. Okay, so you might think it has a minus right here, but we won't have it. So we need to find the modulus, right? R is the modulus, which is the square root of the real component. The real component is 0, plus the imaginary component, negative 4. Right, 0 squared, this just becomes 16, and the square root of 16 is 4. And then we need to find theta. So that's r. To find theta, we can just plot it, right? It's negative 4i. What angle gets us to here, right? The real component is 0. The imaginary component is negative 4. So we can say 270 degrees. We can say 3 pi over 2. We can say negative 90 degrees. I think it's standard to use an angle between 0 and 360. We'll say theta is 270 degrees. So, in polar form, we'd say it's r, which is 4, times the cosine of theta, 270 degrees, plus I times the sine of theta, which is also 270 degrees. And that's our answer. Or, right, if you wanted, you could run out of lead on your pencil. If you wanted to use a shorthand, what that would look like is r, which is 4, cis theta, 270 degrees. These both mean the exact same thing. Right? It just depends on what, obviously this thing on the top is a lot more writing. And be very careful here. Be very careful, because what you might want to do is simplify and say, we need to simplify, right? What's the cosine of 270 degrees? But you really don't want to simplify. And again, I'm running out of room. But do not simplify this. I'm curious if anyone knows why we don't want to simplify it. But I'm not going to tell you yet. Okay, this is polar form. This is what polar form looks like. And this is what the answer wants. If you don't know why you don't want to simplify it, we'll find it out soon. Kind of funny. Well, it's funny to me. Okay. So we can keep on going. Do part B. Z is negative 4 plus 4i. We do the same thing here, right? Our answer is going to be r times the cosine of theta plus I times the sine of theta. We just need to find r and theta, and then we'll be done. So r is the modulus, square root of the real part squared, plus the imaginary part squared. Let me just simplify that. 16 plus 16, square root of 32, which simplifies to 4 root 2. If you don't remember how this happens, remember you can write the square root of 32 as the square root of 16 times 2. The square root of 16 is 4. The square root of 2 is the square root of 2. That's what's happening here in this step. Always remember to simplify your square roots. And then to find theta, we can just get a little graph, right? The real part's -4. The imaginary part's +4. And you don't have to have a super fine graph, right? All you need is a little triangle. Here's the point. This is -4. This is +4. We need to find that angle. So there's a couple ways of finding the angle, but somebody tell me, what is that angle, or what is something we know about this triangle? Yeah, exactly. It's a 45, 45, 90 triangle, right? So this little thing down here is 45 degrees. The reference angle is 45 degrees, so that means that theta must be 135 degrees. You could also use inverse tangent, yeah, right? What you could have done is say, okay, what is inverse tangent here? A 4 over -4, or 4 over +4, to get the 45 degrees that way. This is one of our special triangles, so just recognizing it's 45 degrees will work. But if you have more complicated triangles, you will have to use that inverse function. Good. So we found theta, we found r. We're just going to say that z is r, which is 4 root 2, times the cosine of theta, which is 135 degrees, plus I times the sine of theta, 135 degrees, and this will be our answer. Or again, if you want to write it with a shorthand, it would look like 4 root 2 cis 135 degrees. I'll take either one. Yeah, it's special. Just like all of us. And again, we don't want to simplify this. And now I'm going to show you why we don't want to simplify it. With example 4. All right, express in rectangular form. Z is equal to 12 times the cosine of pi over 6 plus I times the sine of pi over 6. So this is in polar form. And the reason why we don't want to simplify it here is because if we simplify this, it turns it into rectangular form. So if we simplified it in part B, we would have gotten all the way back to the beginning, and we would have gone in a circle. It's a good way to check your answer, but it does waste a little bit of time, or use a little bit of time. Let's not say waste. Okay, so right? To do this, just simplify. And it turns into rectangular form. If you don't believe me, you're going to see it right now. All right. So, cosine of pi over 6, we can use our 30, 60, 90 triangle. Cosine of pi over 6 is root 3 over 2. Plus I times the sine of pi over 6, opposite over hypotenuse, 1/2. Now we distribute. 12 divided by 2 is 6, so this becomes 6 root 3. 1/2 of 12 is 6. That's what it looks like in rectangular coordinates. Okay. So to go one way, it's a lot quicker than going the other, right? Going polar to rectangular is just simplification. Going rectangular to polar, you need to find what your R is, what your modulus is, what your absolute value is. You need to find your angle using trig, and then put it in the form. Easy, you betcha, Lucas. How you doing? So now we're getting to the really fun stuff. Okay, now we're getting to the stuff that makes me happy. And remember, you're not going to have to remember all. Remember, you don't have to remember. Remember, you don't have to memorize all this crazy stuff that's about to happen. You do have formulas in your chapter 10 formula sheet. Let's go. Example 5. This is where the fun begins. Multiply Z1, let's call that R1 cis theta 1, Z2, which is R2 cis theta 2. What happens if we multiply these things together? Watch this. This is going to be a little tedious. This is like an exploratory problem. We're going to have a formula to do this, but I'm going to show you where the formula comes from just now. So you just want to sit back, relax, and watch the magic. Go for it. We'll do some more regular example problems after this. So Z1 times Z2. Let's write it in the long form, right? It's going to be R1 times cosine of theta 1 plus I times sine theta 1 times the other one, R2 times cosine of theta 2 plus I times sine of theta 2. Right? That is just, this is R1 cis theta 1. This is R2 cis theta 2. So we're going to have to FOIL these insides. But the R's can just multiply. These can just all go out in front. So let's put the R's in front, R1, R2. And then we have to FOIL these insides. So are you ready? This is going to be cool, okay? We get cosine of theta 1 times cosine of theta 2. Outer. Cosine theta 1 times I sine theta 2. Inner. I sine theta 1 cosine theta 2. Last. I squared sine theta 1 sine theta 2. I squared is -1. You get minus sine theta 1 sine of theta 2. And you might be saying, Jason, why the heck are you getting so excited about this? Why are you getting so excited about this? There's nothing to be excited about. Well, I'll answer you. I'm going to show you something. Okay? Remember this thing over here? You remember this little identities.pdf? There were these things that we called the sum and difference formula, right? Sine of one angle plus another angle is sine u cosine v plus cosine u sine v. Cosine of the sum is cosine cosine minus sine sine. That's exactly what we have here, right? Look at this. Look at the red. Cosine theta 1 cosine theta 2 minus sine theta 1 sine theta 2. All right, what is that red stuff? That red stuff is just cosine of theta 1 plus theta 2. And then over here we have an I, right? Cosine theta 1 sine theta 2 plus sine theta 1 cosine of theta 2. That is just the angle sum for sine. So to multiply complex numbers, listen to this. This is crazy, right? To multiply complex numbers, you just multiply their lengths and add their angles. No foiling necessary. To multiply things geometrically, you just multiply the lengths together and add the angles. That seems ridiculous to me. And again, let's say hypothetically, you don't feel so passionate about this as I do. I think this is really cool. And say, I'm not going to remember that, Jason. Well, you don't have to. Chapter 10 formula sheet right here's got it right there for you. To multiply two complex numbers together, multiply their lengths and add their angles. All right. So that's pretty neat. That's pretty neat how that works. So this is just showing you where it comes from. If you FOIL it out, you use angle sum, and that's where it comes from. But to actually use it, it's much easier, right? Watch this. I'm going to do this super fast. Example 6. Multiply. It's going to take longer to write this problem down than it's going to take to solve it. Z1 is 4 cis 80 degrees. I'll use this shorthand because I don't want to write it all down. Z2 is going to be 2 cis 145 degrees. So watch this. Watch how fast this goes. Multiplying two complex numbers. Z1, Z2. Multiply the lengths. 4 times 2 is 8. And add the angles. That's 225 degrees. We're done. There's no decision that's been made for the fall semester yet. It just depends on how the world looks. But as for now, the plan is to meet face-to-face in the fall. Isn't this crazy? Look how quick that was. You don't have to FOIL complex numbers, right? Before, to multiply complex numbers, right? It was super annoying. You had to FOIL it out. You had to simplify. This is like that. And that's one of the things that I love about math. Is that so many things, like people didn't make this up. People discovered this. This is just how numbers work. It's not like some guy said, well, let's make complex numbers this way, and then we're going to make polar form this way, and then let's have algebra work this way. No, it's just the way it is. And that's exciting to me. Okay? So there's a whole bunch of formulas here. The shortcut for multiplication is this. You just add the angles. The shortcut for division. You just divide the lengths and subtract the angles. It's so easy. You don't have to multiply by the conjugate and FOIL and simplify. Super quick with polar form. We have something called de Moivre's theorem, where if you have a complex number raised to an exponent, you just exponentiate the length, the modulus, and then multiply the angles. The roots of complex numbers, that's a little messier. I want to make sure we have time to do that today. Okay. So real quick, right, we can divide really easily as well. Z1, let's say that's 2 cis 213 degrees. Z2, let's say that's 4 cis 33 degrees. So to divide Z1 divided by Z2, right, it's super easy. You just use the formula. One warning though when using the formula, right, you divide the lengths, you don't divide the angles, you subtract the angles. So don't be lazy. Check the formula sheet every time, especially on like a quiz or exam. Make sure you're using it correctly. Okay, so What's 2 divided by 4? That's 1/2. What's this angle minus this angle? 180 degrees. Just like that. One step that you can do in your head. Well, you might want a calculator for subtracting those angles. But I just think that's crazy. Like how quick and easy it is to divide these things. Also, if you're curious of where this formula comes from, right? I showed you where the multiplication one comes from. If you're curious where the division one comes from, you actually divide these numbers, and then you have to divide them like we usually divide. You would multiply by the conjugate of the denominator and simplify, and then you'll get some more identities. Okay, let's use the power formula. Simplify 1 plus I to the 10th power. There's something called the binomial theorem, which makes this a little bit more manageable. But this would be terrible to do in rectangular forms. Right? Rectangular form, blech. Not good. But if we write this in polar form, it becomes a lot easier. So, let's write this in polar. Yeah, exactly, Cinna. You understand. So everything's easier in polar form, except for maybe addition. Addition, all right, addition is easier in rectangular form. But who wants to do addition anyway? Addition is so a couple years ago. So again, we need to find R, the modulus. Square root of 1 squared plus 1 squared. Square root of 2. We need to find theta. 1 plus I is right here. I just drew the world's smallest triangle, so I apologize. You probably can't see this. This is the smallest triangle I've ever seen in my life. That's a lie, but it's pretty small. Again, it's 45 degrees, right? These two sides are the same. So, what do we have? We have 1 plus I to the 10th. Complex numbers, right? Complex numbers arise in signals. I knew they were there in electrical engineering. I'll have to research that. That'll be good. It's obviously good when I know where they arise, so that when students ask me, I can tell them. So, right, this is just, what is 1 plus I? It's R, which is the square root of 2, cis theta, which is 45 degrees, still to the 10th power. And then we use de Moivre's theorem, which says if we have a complex number raised to the nth power, we just raise the modulus to the nth power and multiply the angles by n. Okay, so it's going to be the modulus square root of 2 to the 10th power, and then the angles just get multiplied by 10. Like so. And now we just simplify. Careful here. Square root of 2 to the 10th power. If you remember rational exponents, you can make this a little easier. This is square root of 2 is 2 to the 1/2 power raised to the 10th. And this just becomes 450 degrees. And now we just multiply these, right? 1/2 times 10 is 5. And let's not use 450 degrees. 450 degrees is too big. That's not too big, but we can make this look nicer, right? 450 degrees is the same as 90 degrees. Right? 450 minus 360, it's just 90. So we have 32, 2 to the 5th. So it's 90 degrees. And that's our answer. If you wanted to answer in rectangular coordinates, you could as well. Right? This is 32 times cosine 90 degrees plus I sine 90 degrees. Cosine of 90 degrees, that's the x coordinate, is 0. Sine of 90 degrees, that's a y coordinate on the unit circle, which is 1. So it's just 32i. And this took more steps, right? But I guarantee you, converting it to polar coordinates is a lot faster than multiplying this out 10 times. All right. No foiling necessary. That's how you do powers. Okay, we have 8 minutes to talk about the last thing. The last thing's a little confusing, okay? So the last thing is, how do we find roots of complex numbers? So a lot of times we think of square root as a single thing. The square root of 4 is 2. But there are 2 square roots of 4. 2 and negative 2 are both square roots. There are always 3 cubed roots of any number. There are always 4 fourth roots of any number. Okay? And if you're doubtful on how that works, it has to do with the definition of a square root. The definition of a square root is a number such that when you square it, you get b. Right? So negative 2 and positive 2, when you square them, you both get 4. There's always 2 square roots. And then most people have seen this before. But there's also 3 cubed roots. There are 3 numbers a such that when you cube them, you get any number b. And sometimes they're complex. We're going to talk about how to find them all. And that's what this last thing is about. Okay? You just take the root of the length. And then this looks super confusing. But let's just do a problem. And you'll see that this inside's not as confusing as it looks. All right? Let's do number 9. Right, find all the fourth roots of part A. Z is equal to 16 times the cosine of 120 degrees plus I times the sine of 120 degrees. This number has 4 fourth roots, and we're going to find them all. So we're going to use the formula. Okay, let's write the formula down again. So this says that the fourth roots, dang it, that all fourth roots, the formula, we're just writing it down again, are going to look like r to the 1 divided by n times the cosine of theta over n plus k times 360 degrees over n. We're just copying down the formula. Plus I times sine of the same thing. Okay? Where k is 0, 1, 2, all the way up to n minus 1. So let's just write everything here. What is our r? Right? R is 16. What is our n? We want the fourth root. So n's going to be 4. Theta, we know that too. That's 120 degrees. We found r, n, theta, and yeah. We haven't talked about k yet. K goes from 0 to n minus 1. So k is 0. What's n minus 1? N minus 1 is 3. So k is 0, 1, 2, and 3. They're going to be 4 k's. And that makes sense, right? 4k's, 4 fourth roots. So let's just plug everything in. R is 16. N is 4. Cosine of theta, 120 degrees, divided by n, which is 4, plus k. K is 0, 1, 2, and 3. Let's keep k as k for now. Right? Times 360 degrees, divided by n, which is 4, plus I times sine of... You can write it all again, but I don't see any reason to write it all again. It's just the same thing. Okay? Or if you want to be doing this in cis notation, that shorthand, it's a lot quicker in cis notation. We'll do that for part B. Okay? So we just simplify now, right? The fourth root of 16 is 2. Times, what do you get? The cosine, 120 divided by 4, that's 30 degrees. 360 divided by 4, that's 90 degrees. $30 plus 90k. Right? And again, k is 0, 1, 2, and 3. So to find all the fourth roots, we just use 0, 1, 2, and 3. So when k equals 0, what do we get? We get 2 cis. When k is 0, 30 plus 0, 30 degrees. When k is 1, what do we get? 2 cis, 30 plus 90 is 120 degrees. When k is 2, we get 2 cis, 30 plus 180, 210. And the last one is going to be 2 cis when k is 3, 30 plus 270, 320 degrees. So these are all the fourth roots. And you could check your answer if you wanted, right? If we raise all of these numbers to the fourth power, we should get our original thing. Let's check, right? Let's just check 1. What is 2 cis 120 to the fourth power? Well, we used De Moivre's theorem, which says that it's going to be 2 to the fourth power, which is 16, times cis. We just multiply these according to the formula, right? De Moivre's theorem. Exponentiate the modulus and multiply the angle. That's 480 degrees. Is that what we started with? Well, just subtract 360. 16 cis, 120 degrees. Yeah, I want to do one extra problem before the end of class. We'll go a little late today just to do one more problem on this stuff. If you want to head out, you can for extra credit for today's attendance. Give me the name of a season. It could be your favorite season, but it doesn't have to be your favorite season. The name of a season. Summer, winter, spring, fall, autumn. If you want to say autumn instead, you can say autumn. That'll be the extra credit point. For today, we're going to do one more problem though. Okay, so again, because this is the original problem, that's how we know that at least this answer, we checked one of our answers. We could have checked all 4. At least this answer is good. Okay. There's a lot more to talk about this, but we don't really have that much time. So I'm just going to do one more problem. Part B. 8 cis 3 pi over 2. So the formula, right, this is in radians. The formula is in degrees. You can just convert this to radians, right? 360 degrees is just 2 pi. So all the fourth roots right? We can just copy down the formula. It's r to the 1 over n times the cis theta over n plus k times 2 pi over n, right? So r is just 8, so we get 8 to the 1 over n. N again is 4. Cis theta is 3 pi over 2 divided by n, which is 4, plus k times 2 pi over n, which is again 4. And k is 0, 1, 2, and 3. It goes up to n minus 1, and n is 4. So this is the 4th root of 8, which doesn't simplify this time. But the inside simplifies. 3 pi over 2 divided by 4 is 3 pi over 8. This becomes pi over 2 times k. And then we just plug in. K is 0, k is 1, k is 2, and k is 3. So what we're going to get is the 4th root of 8. Cis, when k is 0, we just get 3 pi over 8. When k is 1, we get this plus pi over 2. Is this plus 4 pi over 8? 7 pi over 8. When k is 2, get the 4th root of 8. Cis, k is 2, we get plus pi, which is 8 pi over 8. And the last one is when k is 3, which will be 3 pi over 2, which is 12 pi over 8. And those are our 4 answers. Again, if it were cubed roots, you'd only have 3 answers. K would be 0, 1, and 2. If it was 5th roots, you'd have 5 answers. 0, 1, 2, 3, 4. Okay, so you have as many answers as what kind of root you have. All right, and that's it. That's everything. Okay? That's the whole section. We'll do a Zoom review on Monday. Stay tuned for the invite. I'll send it on Canvas and Discord, where you can ask questions, or I can just do review problems as people prefer. And your final is going to be on Wednesday. Okay? Good luck. If you have questions, please ask, and have a good weekend.